Okay. We will go through some of the homework. Essentially, what are you supposed to do? And hopefully that reduce some of the confusion that potentially can happen because this is like kind of like the first time. It's not non-trivial. It's not straightforward until like what you're supposed to do here. It's a simulation. It's not an actual. Well, it's an actual program, but now you're modeling a real CPU. So once we're done with the lecture on pipelining, we'll go through some of that as well as the in-class exercise. The in-class exercise this time is going to involve what we learned from Monday and as well as basically Monday and today. And today we're going to cover the concept of pipelining. This is one of the really basic concepts, if you will, in many task-based program, including how you design processor, and this is actually used a lot in everyday life, right? I'll tell you why and how, but the motivation behind this is if you think about how data paths are being used, right, in the multi-cycle architecture. I said this is basically you try to fetch the instruction. When you're trying to fetch the instruction, so during the fetch, what is being involved? You send the address to the memory, right? You send the address to the memory. The rest are like emptying, not doing anything. You're trying to get something from memory. So while you're spending time fetching this instruction, the decoder is free, the register file is free, the ALU is free, everything is idle. When you're decoding what is the instruction am I supposed to run, supposed to process, right? The fetch unit is idle. The ALU is idle. Everything else but the decoder is idle, right? If you if you basically follow this same logic, right? When you execute the instruction, in the ALU, the memory is idle, the decoder is idle, the fetch bandwidth is idle, like you're not using anything there. So these mean when you look at your processor, a lot of things are not utilized, right? You're only utilizing a fraction of your entire CPU at a time, right? So the idea is like, what? Let's say I'm basically doing an add in the execute stage right now. Like so let's say I'm oops, 10. So let's say I'm executing, right? The add, right? For instruction n, it means that the fetch is empty. I'm not doing anything to fetch the new instruction. I'm not doing anything to decode an instruction. It's not doing anything. It's idle. So why can't I use that idle resource to get the n+1 instruction n+1, the next instruction, right? And that's the concept behind pipelining. Any questions so far? Any questions so far? Basically, while you're processing instruction n and it's trying to do an add right now, the rest of the CPU are not doing anything. So why can't we use that? And pipelining 101, I'm gonna use the example that basically my professor at SMU used it because I feel like this is a perfect example. How many of you have to do laundry on your own? Yes, no? Basically, when you need to do laundry, right? You first need to wash your clothes, then you dry it, and then you fold it so that you can use the clothes that you wash later, right? And this has to be done in order. You can't dry it and then wash it and then fold it. It's gonna end up into this weird soggy piece of clothing which you can't use, right? So the way you do this, right, is has to be first of all in order: wash, dry, fold, wash, dry, fold. Each one of these steps takes its own amount of time, but these are the tasks you have to do when you have to process your laundry, right? And let's say you haven't do laundry in a long time. You've been like slacking off, and you actually have 5 batches of clothing, right, that you need to put in the a laundromat, and Essentially, you can only fit in only one batch at a time. And you have enough money to buy one washing machine and one dryer, right? And then the washing machine takes 30 minutes per batch. Dryer take 1 hour per batch, right? This is actually, if you have to do this, usually that's roughly the time. Dryer would take longer. And then moving between the washing machine to move all the clothes to the drying machine magically takes no time. You have the magic thing that can move the clothes around, and folding the clothes is 30 minutes. So how many minutes in total that you have to spend to wash, dry, and fold all 5 batches of clothing? Any taker? It's just adding a bunch of numbers together. So how much time do you have to spend here? If I only have one washing machine and one dryer. So yes, like roughly 10 hours, right? Each batch, which would take 2 hours. You wash 30 minutes, then you dry it 1 hour, and then you fold it in 30 minutes. So you have 5 batch. At the maximum, this should be within 10 hours, right? Within 10 hours. That's our ceiling. Can someone tell me, can I do better here? Can I do better job at doing laundry? Okay, so let's answer the first question. Is it possible to use less than 10 hours? Yes, right? Obviously, you can spend less than 10 hours on this problem. Uh, how? Okay, yes, actually that's one way. We call this Superscalar. You buy more dryer and washing machine. Yay, right? So if we have 5 dryer and 5 washing machines, obviously it will take 2 hours. You put everything in wall and then you stop at a folding. We will talk about that a little bit later. Basically, if you buy 5 washing machines and 5 dryers, then washing and drying would take uh 1.5 hour, and then because you're the only one doing the folding, you fold 5 batches that take in total 2.5 hours, which means that in total you can spend 4 hours on this, right? Another way you can make this faster is called pipelining. What does pipelining do, right? So one thing that you can do here is, while you are, so this is the first batch, right? So you wash it, right? This is 30 minutes. The next thing after you wash it, you need to dry it, right? And then you fold. This is 1 hour and this is 30 minutes. When is the earliest? When is the earliest that my washing machine becomes free? After 30 minutes, right? So basically for our second batch, you can actually start washing right here, right? And when can I dry it? 30 minutes after this point, right? 30 minutes. So this is, the drying machine is still busy with the first batch. So you dry it here. And then you fold it, right? So this whole thing is 1 hour and this is 30 minutes. So at this point, how much time has passed at that point that I have the dashed line here? Actually 3 hours. This is 30 minutes. This is 1 hour, right? This is 1 hour and this is 30 minutes. So this is in total at the 3 hours mark, right? So now you finish 2 batch in 3 hours instead of 2 hours. Let's continue on. Third batch. When is the earliest time that I can wash it? Right here, right? When can I dry? At what minute mark? is right here, right, which is 2.5 hours. Because the drying machine is still on the second batch until 2.5 hours. So it's right now at 2:30, you can dry. And this finish at 3:30 and then fold. So this is 4 o'clock, right? 4 hours in. For the fourth batch, right? So you can wash it here, and then you have to dry it right here, and then fold. The fifth batch, wash it here, and then dry it right here, and then fold. So how much time in total am I spending? 6 hours. Yep. So if you add everything, this is right at 6 hours. You just basically make it about almost twice as fast, right? My next question, which is kind of like addressing what Brandon suggests, if I have the money, what would I do? What's the first thing that I would buy? Dryer, right? So if you have two dryers, this is what would happen. The first batch, wash, dry, fold, wash. Because you have the second dryer, so this is here, dry, and then fold. Then you can wash it here. Then you dry it here because the first dryer is done, right? And then fold. Wash, dry, and then fold. So you can basically overlap completely, right? How much time do I spend here now if I just buy one more dryer? Basically, each small box is 30 minutes. Each big box is 1 hour, right? So it's actually 1, 2, 3, 4, 5, 6 small box and one big box. So that's basically down to 4 hours, right? You buy one more drying machine and you cut the time to 4 hours. So this is the concept behind pipelining, right? Basically, I have a resource that I idle. I have a washing machine that I'm not using, so I can start doing the next batch. Think of the instruction as a batch. Any questions so far with this example? So my question, how can you tell, right? If you have the money, how can you tell which resource are you going to add, right? In this case, if I have the money, what do I buy? How can you actually determine that? Basically, you look at the critical resource, right? Where at some point everyone needs it, right? Look for the thing, yes. Look for the thing that give you the most waiting time because if you add that resources, less people would wait for a shorter amount of time because you have a second one. Uh, this is important when you design a processor, right? Because if you look at all the components, everything combined, something like this, right? So if you look at processor design, over here, if I say the memory is the slowest, right? If I say the memory is the slowest, what would I do? Get more. I think you got the right track. What would happen if I buy more memory? I'm just gonna create larger memory, right? What I want is the ability to go to the memory more than like service more than one request at a time. Have you heard about the DRAM bandwidth? when you look at bandwidth, right? So, okay, what is a bandwidth? Bandwidth, whenever you talk about bandwidth, everything in computer science, everything in computer engineering, whenever you talk about bandwidth, think about it as you have a pipe, right? It's the amount of content you can push through given the amount of time. Internet bandwidth, let's say you have 100 megabit per second. It means that within 1 second, I'm giving you the ability to push through 100 megabits of data within 1 second. I'm not telling you how fast it is. I'm not telling you how fast the data would arrive, but I'm telling you how much I'm going to give the actual volume, right? So over here, one thing you can try is get more bandwidth to the main memory, allowing a lot of things to access the memory at the same time, right? So that's one thing you can do. I'm getting sidetracked here again, but let's come back to pipelining, right? Pipelining. What is the main steps when you process the instruction? You have fetch, right? You have fetch, you have decode, you have execute, right? And then you might have to access the memory and write back, right? So we have these 5 steps. Are you all with me? Basically, you have 5 steps. You first fetch the instruction. You figure out what am I supposed to do with my instruction, which is called decode. Then once you know what you're supposed to do, actually run it, execute memory, execute and dealing with memory. And then the last step is write the result back so that you move from data D1 to D1 prime, right? So fetch, decode, execute, memory, and write back. So we can design our pipeline that way. You have the fetch unit. And the first step is you go fetch the data, then you decode, right? So in the decode stage, you basically handle everything in here. You are trying to decode what the instruction is doing. You try to access the register files. Then the next step is you're gonna execute the instruction. Okay, so anything that has to do with the ALU would be done in this step. Then you hand it off to the memory. If you need to access memory, you go to access the memory. And then write back. Write back means I'm gonna update the next PC. I'm gonna update the results, right? Each one of this would handle each instruction. Right? So let's say instruction N is in the execute stage. What instruction would be in the memory stage? If I'm trying to execute instruction N in my code, in my assembly line N, what line would be on the memory stage? N-1, yes. So this would be instruction N-1, right? How about write back? That's going to be instruction N-2, right? And over here, you are trying to decode instruction N+1, and over here, you're trying to fetch instruction N+2. Are you all with me? Basically, if you look at this pipeline, it's like you are washing the clothes, right? If the batch N is in the dryer, batch N-1 would be folding, you're folding batch N+1 and you're trying to wash batch N+1, right? Same thing here. Everyone with me so far? Yes, no? Okay, perfect. All right, so now we would start to have to discuss, wait, there are some issue here, right? Because the programmer would see whatever you commit and write it back. So if you're from the programmer point of view, instruction you are seeing right now, if you're the programmer, remember the programmer see the changes of my instruction, right? So what is the last instruction I just finished? What's the last instruction I just finished? Actually, it does not end. Because why? Programmers see the content of what's in here, right? What's in the register files, which means that The last instruction that modify the register file and the PC, the red thing, is n minus 3, right? N minus 3, because that's the last one I just finished. So the programmer would see whatever n minus 3 is doing. In the next cycle, they will see n minus 2. In the next cycle, they'll see n minus 1. Are you all with me so far? Basically, from your programmer point of view, if somehow this code, if your program crash and you want to debug, right? If it crash at this instance of time, you will see n minus 3. That's the last instruction. So what does that mean? If the programmer see n minus 3, it means that somehow you need to have a bunch of temporary variable, right, to store anything in the middle. You need to have a way to store, okay, I'm processing n minus 1 in the memory stage. So this is the current data related to n minus 1. In the execute stage, instruction n, right? So you need to store intermediate data. It's like having a temporary variable in your program, right? So basically, the programmer point of view, you will see it after you finish the write back. Anything that happened before the write back, you need to figure out what you do. What would you show the programmer? We'll discuss that issue in the next, not next week, next 2 weeks. But let me kind of summarize the key issues. Basically, over here we have 5 stages. Right? This is a classic 5-stage pipeline. So if you see the word 5-stage pipeline in textbook, they're talking about fetch, decode, execute, memory, write back. This is like a classic textbook processor design. If you have 5 stages, it means that each one of these has to handle different instructions, as I said, right? N minus 2, n minus 1, n plus 1, and n plus 2. So it means the design needs to somehow process. Basically, you have to process 5 instructions at the same time. Where, let's say the fetch is doing an instruction n, decode would have to process n minus 1, execute n minus 2, memory n minus 3, and write back n minus 4. And as I said, this is what the programmer, that's what visible to the programmer. Right? After n minus 4, which is n minus 5, that's what visible right now. Why? Because you update the changes during the write back. You update the PC, you update the register files during the write back. Other states have to somehow store the intermediate value. Y'all, are you all with me so far? Do you have any questions, or do I anything you confused about, or are you confused and you can't explain why you're confused, so I can try to reiterate the same issue again? Please tell me. So your question. So let me rephrase your question, because I want to make sure I understand your question correctly. Basically, what you're asking is, if you look at the programmer state, like the one that's visible to the programmer as instruction n, right? Are you asking why does n goes backward? So let me put it this way: n is just a random number, is a relative value, right? So let's say fetch is handle instruction 6 right now. It means that the code would be the earlier instruction, that instruction on line 5, and this is line 4, line 3, line 2 on your assembly, right? On your assembly code. It means that right now the only instruction that fully finished is instruction 1. Instruction 1, the first line in your code, that's the only one that's fully finished. That's what the programmer would see. That's what's visible to the programmer, because it passed the write back, it see all the changes, so you see the full changes that come from instruction 1. For the instruction 2, 3, 4, 5, and 6, they are still being processed. They are still being processed. Basically, you need to wait a little bit more until instruction 2 finish. A little bit more to finish instruction 3, and way more for instruction 4 and 5 and 6. Right? And from the programmer point of view, right? From the programmer point of view, you want to make sure that you see the fully committed instruction. Does it answer your question? I just want to make sure that it's clear for you. Okay, cool. So basically you want to see the full changes, the full I finished processing this instruction. That should be what is visible to the programmer. Right? We'll discuss a little bit more in detail about like this, as I said, in the next 2 weeks. But to actually support it, it means that you need to somehow remember something in the middle. Right? We call this pipeline register. Think of the word register as temp variable. Right? When you use the register in the program in assembly, you're trying to use it as a variable in the middle that you need to store value. Pipeline register is basically a temporary variable that I use to store intermediate steps. Right? So anything that has intermediate value dependent on that instruction has to be stored. You save it, right? You save it so that it can go through the pipeline. Why do you have to save it? The reason is because register files and PC only reflects what is in the write back, right? So the pipeline register has to kind of store all the intermediate states, and once you fetch, everything that relate to the fetch is stored in the pipeline register, and in the next cycle, those values get forwarded to the decode. Then in the next cycle, that gets forwarded to the execute. Each of these internal data would be the internal data related to that particular instruction that are running on that state. And obviously, because you're adding a lot of things, right? This can be costly. You need to store intermediate value. You need to think of, okay, performance versus diarrhea. Most of the time, I would say most of the time, actually all of the time these days, you have enough transistor to support this. So every single CPU would apply pipelining. Back in the day, maybe not, depending on how you want to design it. These days, if you look at the normal CPU, you're going 30, 40 stages easily. Right? And here's what happened when you put the pipeline register. I would denote it as this vertical red box, right? Vertical red box. And every time you have like a data go across the red box, right? Something like this, right? This thing, these data and address, these output, right? And then all the select over here. Whenever you try to select, depending on the input right here, right? It has to be related to the instruction you're running. If the select is for instruction n, pass it around the whenever instruction. Let's say you're moving instruction n from execute to memory, right? From execute to memory. Everything, the data, the address for instruction and specific to instruction n has to be moved to the next stage. And then you move n plus 1 from decode to execute. Basically, you need to make sure you remember the right value, not one instruction earlier, not one instruction later, just that instruction. And every time the clock ticks, every time you progress in time, you move the data into the next stage. Right? Give me 1 minute. I need to take this phone call. So I'll be back in 1 minute. Is that okay? Right, sorry for that interruption. I'm back. Basically, whenever you have this pipeline register, move everything related to the instruction along with the stages. That's the key because that is what you have to do in assignment too. Make sure you move it around. Don't leave something behind. If you leave something behind, your code will become buggy and you have to figure out which one did I forget. Basically, just don't make sure you don't forget anything. My suggestion is if you draw things out on a piece of paper, it helps a lot because basically once you have everything in stages, you will see what cross which line. Whenever there's an arrow crossing two stages, it means you have to move those things around. All right. So how many people here have a question of like, so then if having more stages is good, how many should I have? How many stages should I add? So yeah, the guideline is kind of like that. When you move the instruction, move the value inside the pipeline register to the next stage. That's it. Basically, don't forget to move them. Think of it this way. Uh, Whenever you have pipelining, right, you are trying to move the instruction across the stages. So everything that related to instruction n has to be moved across the stage as well. And that's it, right? So the next issue is when you add more stages, let's say you change from 5 stages to 30 stages. What do I shrink? What do I shrink? Basically, I shrink over here. If you look at the diagram, right? If I somehow make one more slide over here, right? I shrink the fact that I have to move an electron from here to this distance, right? I just cut that distance in half, right? Which means that the time that it takes to move the electron from one place to another would be lower, right? Because you just shrink the distance, which means that you can have faster clock. You can clock your CPU faster. So are you all with me? Basically, if you have more pipeline stages, there's a likelihood if you do it well, you can make your clock faster. It's also enable more structure to be active all the time, right? You have higher utilization. Parts of the logic that involve in the adder can now process two instructions. So what are the downside? What are the downside of having more pipeline stages? Anyone want to take a guess? You need more register, which means you need more die area, right? You need to consume more power. The design is more complex, right? Because you need to sort of figure out, okay, where do I make a cut? If I make a cut right there, what do I save? How do I move everything? And what if there's a branch? What if there's a jump, right? You move the instruction somewhere else. You don't do line by line by line. You run into if else, so you have to jump to the else statement. What do you do? We'll discuss that in a little bit. But let's talk about a real assembly code and figure out how many instructions does it take. So the table down here is for me to tell, basically to denote different stage for each instruction over here, right? So with pipelining, how many cycles do I have to spend to execute this code? I'll do instruction one first. I'll do instruction one first. The first cycle, what do I do? For the add, what do I do in the first cycle? Fetch G code, execute, memory, write back. So what stage do I be in? Yes, I'm gonna fetch. And then followed by decode, right? Execute, assume that everything takes one cycle, memory, and write back. Any question for the first instruction? So what is a cycle that can do second instruction? When can I start processing the second instruction? Cycle 2, right? The fetch unit becomes available over here. Yep. So you're gonna fetch, decode, execute, memory, and write back, right? Then this is fetch, decode, execute, memory, write back. Fetch, decode, execute, memory, and write back. So you're done here. Yay, right? You finish the code in 8 cycles. In a multi-cycle architecture, without pipelining, how long would this take? Okay, that's a great question. So does fetch take as long as memory? Usually there are things that we add to make it a few cycles. But in theory, you need to get the instruction from the main memory. If you took system skill and file processing class before, you would realize there's a lecture on caching, right? Caching. We cache the instruction. We actually cache the instruction so you can fetch it from the cache. It's not fetching from the main memory. We call this instruction cache, and it's a really common thing in your CPU. It has to be there, otherwise memory is taking too long to access. So fetch usually take only a few cycles. In a 5-stage pipeline, that's one cycle. So that's a great question. Any other questions here? Okay, so how about this? So what if I say, okay, I'm going to do a multiply. I change the add instruction to a multiply. And then I would say, okay, I only have one multiplier and each multiplier takes 5 cycles, right? Then how long would that take? I only have one multiplier and each multiply take 5 cycles. So instruction 1, fetch, decode, right? And then for execute, how long would the execute stage would take? 5 cycles, yep. So when can I start fetching the next instruction? At what cycle? Yep. And when can I execute? At what cycle? Cycle 8, yes. Why? Because the first instruction take hold of the multiplier, the only multiplier I have, right? So I need to wait until that's done. When can I fetch the third instruction? At what cycle? Cycle 3, yep. And when can I execute that instruction? '13, yes. I'll tell you why. Execute, memory, and write back. The reason why it's at 13 because the pipeline for the execute stage, right, is occupied by the multiply. So you don't have the pipeline register, right? So you have to wait until I free up that last instruction. So over here, instruction 4 fetch, decode, execute, memory, and write back. So this would be done at cycle 16, right? Any question here so far? Yes, you can add. So actually, there are multiple things you can try. Right? First of all, for this multiplier, you can add more multiplier. You can fully pipeline the multiplier, which means that each cycle in the multiply is a different stage in the zone. So the second multiplier can squeeze in, right? So the second multiplier can squeeze in. If you fully pipeline this multiply into 5 different pipeline stages, then at cycle 4, I can put in instruction 2 because the first stage of the multiply is not occupied. The first instruction is not in the second stage of my multiply. If we add more pipeline register, you can kind of like forward the third instruction. You can make it faster, but then you need to make sure that you write back in order because the programmer should see the same sequence, right? Programmer should see the same sequence, which means the write back has to be done in sequence of the instruction. So does it answer your question? Okay, yeah. So there are multiple things you can do. Dealing with so what we call this empty cycle that I can't do anything, we call this instruction stall, right? What does instruction stall mean? It means that I don't have the resource to move instruction through the pipeline, right? The earlier example, I don't have enough multiplier, I don't have enough pipeline register, so I have to stall. The effect is I can't fetch new instruction. If I can fetch new instruction, I cannot move it through the pipeline, so it's going to be slower, right? What are the source? You sometimes don't have enough functional units. Over here, you only have one multiply, but you have 2 multiplication instructions, so you might as well buy one more. Right? Some certain stuff takes longer than others, like memory, for example. Sometimes it takes 50 cycles most of the time. Okay, so what do you do? Sometimes you have the unbalanced design, right? Some unbalanced design. So let's go back to the washing machine. Let's say you have 4 washing machine, 1 dryer, and 1 human to fold it. How many hours that would take? So with 1 washing machine, 1 dryer, one human to fold your clothes, that takes 6 hours. With this setup, how many hours that would take? It's still 6 hours, yes. Even though you add 3 more washing machine, doesn't help you at all, right? Because the drying machine is the one that hold everyone back. So you want more dryers, you don't want more washing machine. This is called unbalanced design. If you run, this is like the concept that goes to every single thing in life, right? If you want to run a company and somehow there's a demand for a team that make the user interface, you want to hire people to do user interface, and that's how you can move forward, right? So you want to look at your design and see what is unbalanced and you address it. What do you do when instruction stalls? There are 2 things you can, well, there are generally a few things you can do, but your goal is to first of all make sure it is correct. Right? Make sure it's correct, otherwise your program becomes buggy. And you need to figure out what value does the pipeline register output. Right? And before we discuss that, let's talk about superscalar architecture a little bit, right? So let's come back to this example. Will this get faster if I add multiplier? Will this code get faster? Yes, exactly, right? You then do the two multiplies in parallel. So the question behind this whole setup is, well, this means that what if I add more fetch unit, more decoder, more adder, more multipliers, or more interface to the main memory, right? This is called superscalar architecture. The only key thing is don't do what we said earlier, buy four washing machines and only one dryer. You need to make sure it's balanced. If you feel like okay, we don't fetch enough instruction, if we somehow can fetch two instruction in a cycle, somehow if that is your bottleneck, go ahead add more fetch unit. If you don't have enough adder, go ahead add more adders. In the GPU, anyone want to make a guess how many multipliers and adder are they having? Tons. More than you can count them. Basically, whatever they said in the CUDA core, in GPU, you notice that they would always love to advertise as CUDA core. The CUDA core are not real actual processor core. It's just the number of ALU. That's how many adder that they provide, how many multipliers they provide. That's the CUDA core. Uh, they would have to one fetch, one decode, and each one of that would have 32 or 64 adder. They'll do that in parallel at the same time. They make an assumption that your program would actually try to do 64 add in parallel at the same time. 64 multiply in parallel at the same time. And that's common in multiple programs like graphics, for example, or machine learning. So Superscalar architecture kind of allows more than one instruction to be dispatched per cycle. This is the concept behind, sometimes you might see this terminology, instruction level parallelism. Instruction level parallelism. It means that I'm going to process more than one instruction per cycle. It exploits the fact that when you write a program, when you write an assembly code, many of those lines are not dependent on each other. You can run two lines at the same time and you see the same results, right? See the same result because there's no dependency. Any question about the superscalar architecture? So if you want to dig deeper in this, in the reading list, it's a paper called Multiscaler Architecture. It's kind of like you put superscalar architecture and the other things in CPU design, inject steroid on that, and that's actually representative of the CPU you buy nowadays. It's one of the really high impact paper on processor design. And if you happen to try to read it out and you have a lot of questions, feel free to check with me. I'll answer that. All right, so let's come back to instruction stall and let's think about what are the causes of these stall, right? Actually, do you want to take a quick 5 minutes break? It's been an hour. I think it's maybe 20 to 30 minutes of content left. So should we take a break or are you guys okay with go ahead and finish it? Yeah. All right. No one say anything. So let's meet in 5 minutes then at 1:08. Is that okay? All right. Cool. Go take a quick break. Think about the things we learned so far, and if you have any questions, type it in. We'll meet in 5 minutes. All right. Okay, one more minute, but let me know if you guys are back. It's only four of you, so well, three of you. The video for this week should be posted in the day. I think WebEx usually these days they're getting really good at pushing the video out after a few hours. All right, are we all back? Okay. Perfect. So this is kind of nice. It's only three of you, so we can ask like, are we all back? And you would just type in. All right. So the cost of instruction solve, well, the first one as we discussed, right, is memory, right? This is still a really big root cause of many programs, and we will talk about how we can deal with some of these. It's still not perfect, but long memory latency can make your program slower. Branch misprediction, which we're gonna go into way more detail on next Wednesday, is another possible courses, right? So let me give you this pipeline again, right? And let's say I have a branch that are in the execute stage, right? Branch if R0 is less than R1. What does it mean? What does it mean? For the next instruction, let's say this is instruction N. How can you tell what would be instruction N plus 1? How can you tell what is the instruction N plus 1? Because I'm going to update my PC either this or this or this or this. I don't even know what's the source of my PC for the next PC, right? So if you have to guess, and I have to fill in the pipeline, what would I do? Which one am I going to guess? Is it PC plus 4 or is it some of these source? If I have to guess, what would I do? I mean, one of the obvious choice is, well, I just get the next line in my assembly code, right? So basically, hopefully most of the time I go to the next line. So instruction N plus 1 is PC plus 4, and instruction N plus 2 is PC plus 8. Let's say that's our assumption. What if I actually jump? What if that is true? If R0 is less than R1, what do I do here? So instruction N is already in the pipeline, right? So you basically need to fetch, right? Basically, it means you need to fetch the jump target. Fetch, if you go to the if else, right, you need to fetch the jump target, which might not be PC plus 4. It means that I'm gonna have to queue this instruction and queue this instruction, right? I am gonna queue two instruction because that's a wrong path. Basically, that's wrong. So I need to queue those two and fetch the correct one. So do you understand what we're doing here? Any questions about this? Basically, if you have if else, if you have for loop, there's a chance that you fill something into the pipeline and you have to we call squash, which is kill that instruction that in the pipeline because you are going to the wrong path. All right. The third thing that can stall an instruction is what we call data hazard. Data hazard. And here's the example of data hazard. Sometimes we refer to this as data dependency. What is unique about the color text in here? Can someone tell me what's unique about the color part here? Yes, it uses the same register from a different instruction. In fact, if you draw this in data flow, this is what happened, right? You have R1 and R2. they get multiplied, right, into R0. These R0 get multiplied again with R4, right, and then the result is R3. Then you XOR R3 and R7, generate R6, right, and then there's a load right here, right, that generate R8, just get add into R0. What does it mean? It means that there are dependency. The red things the first multiply generate R0, which means that the second multiply has to wait until I know exactly, hey, what's R0. It has to wait, right? So let's assume this. Let's assume memory access is 50 cycle. But okay, let's still make sure that we assume fetch. It's 1 cycle. Decode is 1 cycle. There's memory stage. Is 50 cycle. So let's keep this assumption. We'll go through how long my 5 lines of code would take. One quick thing, this is called dependency, and here is a table. So let's go through them one by one, right? So for the first multiply, obvious, right? Fetch, decode, execute, memory. Oh, nope. How many cycles do I spend executing? 5, right? And then memory, and then write back. Instruction 2, when can I fetch? When can I fetch? At cycle 2, right? The same thing. Fetch, decode. When can I execute instruction 2? Yes. Because this is when R0 gets the results. Right? That's after cycle 9. That's when R0 got the correct results, and that's when you can execute, because that's when you can have the correct version of R0. So you're gonna execute, memory, write back. Instruction 3, when can I start? I can fetch here, yes. I can decode here, and then I'm gonna execute here, memory and write back. For instruction 4, fetch, decode, right? Can I execute now? Kind of, yes, but then basically one thing you forget, my pipeline register is full. My pipeline register is full, so I need to wait until I'm done with the earlier execute, because my pipeline register is full. The pipeline register on the execute is still trying to handle at this point. At this point is for instruction 2, right? I mean instruction 1, and then instruction 2, instruction 3 and 4. So instruction 4 has the pipeline register for execute at cycle 18. Memory and so long for now, right? And then for instruction 5, you can fetch, decode, and then execute doesn't start until you finish getting the write back for instruction 4. So do you see the problem of why this would be slow? And how many have you write code something like this? For I equals 0, I is less than n, I plus plus, right? And then you say, okay, a of I equal B of I, and then C of I equal A of I plus B of I. Something like this. How often does it happen? Can you tell me what are the possible data dependency that can arise here? How many places, actually, how many places does data dependency can occur? There's this A of I, right? You generate A of I and you use it right after. Yes, exactly. And then there's I plus plus, right? Where you increment and then you use it to compare. B of I, there's no data dependency on B of I. Why? Because you never modify B of I. Oh, actually, yes, you need to load B of I, but once you have the first B of I, the second B of I is not dependent. You're not reading after writing. Right? So data hazard is something like this, right? So let's come back to this example. These dependency generate the data hazard. If you look through this code carefully, this is read after write. Okay? Read after write, which means that you need to access the value after you just modify the value. And this is a really common problem when you write a typical program. So from the hardware point of view, if the programmer loves to write these kind of things, we need to we need to find a way to deal with it, right? But before we find a way to deal with it, and there's a really easy way to deal with it, but let's break this down into 3 different types. So what you've seen earlier is called read after write. We call this true dependency. It's accessed in any type of processor. Then there's a write after read and write after write. These things happen if you design a processor that is called out of order processor. We will not talk about these two for now. For now, we will not talk about these two issues because the current pipeline processor is in order. In order processor means that I'm gonna run everything in the order of the sequence you see from the assembly code, line by line by line by line. Right? So only raw hazard access, and you're gonna fix this as a extra credit in assignment 2. Right? Assignment 2 will ask you to do pipeline, and you would pipeline using this, using data style. You insert the bubble in case you see data dependency. Your solution is send out empty instruction, wait. Basically, tell wait until I got my results, and then I would continue on. Which means it's going to be slow, right? It's going to be slow, and we can do better. We can definitely do better. Do you understand why this is slow? Basically, if you see dependency, let's wait until it's right back the value, and then I'm gonna continue on. If you look back at our example right here, right? This empty thing is called the bubble. Right? This decode, right? This thing, this empty thing is called bubble. It's an instruction that do nothing. It does nothing because you want to make sure nothing happened because I don't have my data yet. I don't have my data yet. I'm gonna wait until I got my data and then I can continue on to do something. So that's how you can figure out what you can do. Can we do better? Yes. we can do something called data forwarding, right? But before we go to data forwarding, let me actually give an example of what does it mean when I insert a bubble. Let's say I have instruction n here and n plus 1 right here, n plus 2 right here, n plus 3 right here, right? And that's the dependency between n plus 1 and n plus 2. That's the dependency between n plus 1 and n plus 2. The next cycle, I'm going to write it in green color. Basically, you move n to right back. You move n plus 1 to from execute to memory. This thing become bubble. And then n plus 2 and n plus 3 stays there. In the next cycle, I'm going to use the blue ink. Over here, n is done. N plus 1 is here, right? N plus 2 stays here, and then n plus 3 also stays here. Bubble here, bubble here. Nothing is done here. Then in the next cycle, I'm going to use orange. N plus 1 is done. This is bubble, because this bubble move here, this bubble move here. What is in the execute? Is it bubble or is it n plus 2? N plus 1 generate data for n plus 2. So over here, is it safe to move the n plus 2 to n plus to the execute? Yes, it's safe now because n plus 1 commit whatever they want to write to the register file, right? So n plus 2 can move here, n plus 3 move here, and over here is n plus 4. Basically, you stall n plus 2 until it's safe to move forward. All right. This is basically another way you can fix this problem, right? And we'll discuss about this on Monday, but I'll briefly talk about it right now. Observation is sometimes data is available from the execute and memory, right? So why do we need to wait till the write back? My add is done, right? So the idea is, well, we can forward the results in the pipeline, forward to future instruction. Basically, for each instruction, we check the source register and figure out, can I forward the data? If yes, forward the data. And this would solve read after write dependency. And the benefit is CPU becomes faster. Basically, over here, if you're doing n plus 1 and n plus 2 right here, right? And during the execute stage, if n plus 1 generate this dependent data right here, it forward that data here for instruction n plus 2. You automatically forward that ahead of time to the decode. So now in the next cycle, I'm gonna do it in blue. N plus 1 is here. N plus 2, because it now has the data, it can move on right away. We'll go into the detail on how this can be done next lecture. Before we leave today, remember that we have an assignment 1 checkpoint next week. And then I'll talk about the assignment a little bit so you know exactly what to do and what's going on. One more thing, next Wednesday, I have a conflict from noon to 1 p.m. So we can start the class at 1 p.m. Yes, we'll continue for the lecture into 2 o'clock. Then the in-class exercise start at 7 p.m. on Discord. I'll be there to answer your question, but you don't have to, if you finish the in-class exercise, you don't have to attend. It's not mandatory. And in-class exercise 5 is on Canvas. Please go and check it out. But before we finish the lecture part, let me talk a little bit about your assignments. So that concludes the lecture. So let me finish the recording.